Okay, welcome to the today's class. Today it is a lecture number 12. Uh, okay, actually it is actually 12, not 11, because already the 11 is coming, because the numbering actually I forgot to write properly, but this is a lecture number 12. Okay, so let us look at the second order effects. So let's look at the second order effects. Okay. Okay, whenever we talk about the MOSFET is actually a complex device. Okay, so when we are not properly apply the potentials, okay, or the device dimensions properly, if you're not getting that one, so some kind of effects we'll see uh, on a particular MOSFET. That means whatever we have so far we have seen about the current equations on saturation, okay, and body and source are at the same potential we maintain. Okay. And we thought that when VGS is less than threshold voltage, the current is equal to zero. But these kind of things may not be true in some cases. In what cases these are not true, and what are those things we will see now. Okay. So before going to that one, the last class I told you that what is um, the transconductance of MOSFET. Okay. The moment if I give you the transconductance, let us spend some time on this one and we'll go to the next. So for example, this is your MOSFET, right? Okay. So what is the primary aim of this MOSFET for the analog designers? Okay. 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 So when VGS is changing a small amount, okay, how much amount of the current it produces, right? So therefore, how IDS will produce. Okay. That means GM stands for how much change that you can see on IDS by changing VGS provided when VDS is constant. Okay. Okay. So what we derived that equation? So what is the first form that we have seen? Just simply take the ID in the saturation current equation. Of course, this can be observed different places, right? Okay. That means ID is not only the saturation current, linear current equation is also there. So what you can do, if you derive a derivative of this one with respect to VGS, okay, GM under linear. Okay, possibilities there, right? So what is the value? What is this value? We need to derivative with respect to VCS, right? And VCS minus of VT. I told you that you have to complete this one. So what is this value? This value is equal mu n Cox W by L VCS. No, actually, what is the derivative of this one? Derivative of this one is equal to 0, right? Okay, therefore, this is not possible. But the derivative of this one is we take a constant, is VDS is a constant in our case. Okay, we have to derive only for this particular thing, right? Okay, so that is the one actually. So therefore, we need to write anything just like that. It is a derivative of this one is VDS. Therefore, this is what the GM under linear region. Okay. Okay, so our expectation is that the GM should be more. Okay, GM should be more. So when the MOSFET is operated in linear region, is it possible to get the more gain, more GM, transconductance? Not possible. That we have seen in the last class one diagrammatically, we have seen a small change applied, okay, at the linear region. So we'll have very small change in the IDs. But whereas if you are operating this MOSFET in the saturation region, at the same small change of the VDS, okay, you will get the huge change that you observe in the IDS value, right? That's the reason why it is important to measure VCM, GM or in the under the saturation region. What is GM in the saturation region? What we found? 1 by 2 mu n Cox W by L into VCS minus of VT whole square. What we found? What is the derivative of this one? Mu n Cox W by L VCS minus of VT. Okay, the derivative of this one is x squared derivative is 2x. Okay, therefore the half and the 2 will get cancelled. You will get this one. Okay. Okay, what we concluded about this one now? So we concluded that the GM under the saturation region much greater than GM under linear region. Okay. So sometimes the GM is also called as a gain also. Okay. What is this gain is actually transconductance gain. Okay. That means GM can be written in this way. Okay. For example, if you write, what we are applying actually, VGS we are applying. What we are getting, IDS we are getting. So therefore, can we write like this? IDS is equal, actually capital GM into VGS. That's what the better way that we can write. But what is the meaning of the small g and capital G? A little bit later, you consider this as GM. Okay, as simple as that. So therefore, how much the current you are getting? That means what? So GM times VGS. Okay, you apply some VGS. Okay, and there is some gain. GM is available for the transistor. Okay, if you want to say that how much change, how much IDS is changing, means that multiply the GM with the VGS, you will get how much change in the VGS that you will get. Okay, fine. So definitely the saturation is most important for us. This is the reason why the MOSFET must operate in saturation region because of the more current. We are going to use this more current in different places. Okay, to get for amplification, so on and so forth. Okay. Right. Now, this is the one form actually, but there is a different forms that are there for the GM. Okay. Okay. This is the one form, standard form, but GM can also, okay, instead of writing the GM comma S, the GM stands for, we always think about in the saturation region. That's the reason why GM alone I'm writing. So another reason is something like this we can write. So what is the ID here? As we know that this is an ID, right? This is an ID. So in terms of GM, how can I write? How can I write it in terms of GM? This is an ID, right? This is an ID. Can we write this something? How do I write like this? If you take 2 there, can we write this is the GM into VCS minus of VT is equal to 2ID. Okay. So this is all together. So you can see this everything together I have written as GM. With a GM VCS minus of VT whole square, one term that I have to put aside, and something like this everything. So therefore, what I can write now, the GM can also be written as 2ID divided by VCS minus of VT. This is also the second form. This is also the second form. Okay. So in the examination, depending upon what kind of param values they have given, you have to choose one GM, right? If they're given ID value, they have given VCS value, they're given. Just you have to use the GM in this formula. Okay. They have given only W by L ratio. They have not mentioned anything about the W by L ratio. If they have given the W by L ratio and VCS they have given, then you have to choose this formula. Okay. Okay. This is the second form. Okay. This is called the form number 1, F1. And this is called form 2. Form 2. The third form is also there. It's also very simple. We can substitute a VGS minus of VT somewhere. Okay, that means I'll write this one and let me know how we can solve this problem. Okay, the third form is GM is equal square root of 2 mu n C ox W by L into ID. This is the third form. This is the form 3. How can we get this expression? What I have to do? Where I can keep this one so that I will get this option. Any idea? Okay. Take it as a small assignment, okay, and find out this particular one. Okay, it's very easy to get that one. Okay. So the three forms that we have seen, right? Okay. What is the first form? What is the conclusion about the first form? Form 1. What is the conclusion? So GM is proportional to W by L ratio and VGS minus of VT. Agreed? Okay. So what does it mean? If you want to increase the GM of a transistor, what you have to do? You have to increase the gate to source voltage minus the pressure voltage. The drive voltage must be increased. Therefore, the GM will increase. That is the one option. By keeping W by L ratio is constant. Okay. By keeping W by L ratio is constant, change the VGS value more and more, you will get more GM. That is one option. Or okay. Now, form 2, what the form 2 says suggests us that form 2. What is the form 2 can say? So GM is proportional to ID, but it is inversely proportional to VGS minus of VT. So look at, there is a conflict here. You can see in the first case, GM is increases by increasing the VGS, but in the second case, GM is increased by decreasing VGS. Okay, that means you cannot say directly that the GM of the transistor is increases by using the VGS, but you have to think about it. What is the device dimensions, as well as what is the current equation? Okay, so based on that one, we have to say. So if the W by L ratio is a constant, then it is a inverse directly proportional. If the W by L ratio is changing, for example, then ID values also will changes. In that case, it will be inversely proportional. Okay, so you have to remember in this way. So which one make a constant actually? So if you are making this is a constant, for example, then we can say that it is inversely proportional. What is the third form? Form number 3. GM is proportional to square root of W by L or square root of ID. Because mu and Cx, I want to keep it as a constant. Okay. So this is what we can say. Right? Okay, choose properly that which value that you want to change so that the GM will increases. Okay. Right. For example, in this first case, it will something look like this. GM versus of VGS. So this is go linearly, right? Okay, if the VGS is changes, GM also increases, provided W by L is constant. We are not changing the W by L is constant. For example, here if you see the second case, you look at in this way. Let's go and down, okay, with VGS, the ZM, okay. So, and because here is the IDS is constant, we are not changing the current value. But here you can see the VCS, so sorry, it's not VGS, it's an ID, it's ZM, so it will increase. So if the ID values increases, the GM value also will increase, provided W by L ratio is constant. Okay, is the point is clear to everyone? So GM has four values. So the three forms that are there, according to your convenience, you have to use one. Right. This is not the IDS is actually constant. Okay, let us look at that. What is the next one? We have to think about it. Let's take a simple example. Okay, let's take an example. What is the GM? What is the GM of transistor of a transistor when W by L ratio is doubled and when W by L ratio is doubled and VGS minus of it is also doubled. What will happen to the GM? GM will increase or decrease? Decreases. How? See, what is the GM actually? I'm giving the W by L ratio and VGS minus of it. Which form will be suitable? Which form will be suitable? First form. What is this one? Mu n C ox into W by L into VGS minus of VTH. Okay. If I double this one, if I double this and double this one, what will happen to GM? Increases, right? How many times? 4 times. Okay. For example, what is the same GM if I increase W by L ratio is double and ID is also double? W by L ratio is double and ID is also double. What is the value of the GM? Which form is suitable in this case? Third one is suitable, right? GM is square root of 2 times of mu n C ox into W by L into ID. Okay. Therefore, 2 times means that the GM dash is nothing but how many times? It is also it should be 2 times. The 4 is there. Square root of 4 is nothing but 2. Therefore, 2 times of GM. W by L is 2 times and ID is also 2. 2 into 2 is 4. 4 is take it a common from the square root, it becomes 2. Right? Right. Let's take one problem, okay? And then based on the problem, we will see some other insights. Okay, note down. Calculate the bias current. Okay, calculate one problem we'll see. Example number 2. Calculate the bias current of M1 if the drain gate, okay, let me write this particular one. Okay, so one resistor I have given there. Okay, something like this I'm writing. There is a one transistor here. The drain is connected, something like this. Okay, and the potential I'm applying here is in this one. Therefore, this is at 1 volt. This is called RD. Nothing but this is okay. Let me write. This is not the way. Instead of writing this way, this may write in this way. This is 1.8 volts. Okay, and this is 5 kilo ohm. This is NMOS transistor, and this is 1 volt. Okay, and the W by L ratio of this transistor is W by L is equal to 2 by 0.18. Okay, look at this one. What I have given. Of course, this is also, I can simply say, instead of writing, this is the way, the same notation I'm using here, 1.8. Okay, a fixed potential I'm applied at the gate, a fixed potential applied at the drain, and the resistance I have given here, and W by L ratio also I have given there. Assume mu and Cox is equal 100 microamperes per volt square, and VTH is equal 0.4 volts. If the gate voltage increases by, if the gate voltage increases by 10 milliamps, 10 millivolts, what is the change in the drain voltage? What is the change in drain voltage? Did you get this point? The question is that something I have given there. I am changing this value to what? 1 volt plus. I'm changing this 1 volt to 10 millivolts that I'm adding here. Okay, that means 10 plus 1 volt plus 10 milliamps that I have added. Now, there is some kind of voltage here. What is the drain? This is what the drain potential, right? So what is this drain potential change that we can see? Okay. Okay. Now, what is this drain potential here? Can someone tell me what is the drain potential here, VD? So simply it is actually the potential difference between these two, right? Okay. What is this one we can write? See, we know very well that something else we can write. VD, okay, minus of 1.8 divided by 5 kilo ohms is nothing but the current flowing in this particular transistor. Am I right? That is what the current is flowing there. Or otherwise, this VD value plus this potential is equal to 0. If you apply the KVL also, the sum of all the potentials are equal to 0. Or otherwise, simply take the potential difference between these two nodes and resist is available. The current will flow. That current can pass through the transistor. This is how we can write. So accordingly, what we can say now here, what is the VD? VD stands for, what is the VD here? One point eight minus of IDS into 5 kilo. Am I right? 5 kilo. That's what the VDS value. So as we know very well that the transistor is said to be in saturation. Where is the plus? Okay, 1.8, that is there. Okay, this is a plus now. Okay, it should not be plus. Okay, where is the potential flow? Where the current is flowing here. Okay, this is what the wrong thing that I have done. So this is how the current is flowing, right? So if this is the current is flowing, it should be what? This should be plus. Okay, or I can say this is not the way actually. Let me write in a different way. Okay. So this is minus 1.8 minus 1.8 minus of VD divided by 5 kilo ohms is equal to IDS. This is what we can write. Okay. So therefore, what is the value here now? VD is nothing but 1.8 minus is also plus is coming. What is the yeah, that's what I'm so sorry actually. This is actually is going this from 1.8 minus of VD divided by 5 kilo ohms. Therefore, if it is going there, then this will be there. Yes, this is what. Okay. 1.5 there into 5 kilo ohms into IDS. Okay. This is what we can see. Or simply the people will write that this is also in this way. Okay. For example, you write this is the one. This is called 1.8 volts. And this is the source. This is actually at 1 volt. Okay. So if you want to get this potential, simply what we have to do, if you want to get this potential VD, what we can write 1.8 minus of VD. Okay, the potential difference between these two divided by 5 kilo ohms is equal to the current flowing through that particular transistor. Okay, and the same. Okay, that's what we are getting this point. So what, from this one, what we can conclude? So the drain potential is actually, okay, 1.8 volts minus of IDS into 5 kilo ohms. Okay. So if you want to say that the MOSFET is said to be in saturation region or linear region, what is the condition? If you want to say the MOSFET is said to be saturation or linear region, what we should say? We have to compare the gate potential to the drain potential, VGS minus of VT. Did I give this threshold voltage of this transistor? Yeah, 0.4. Okay, so therefore VGS minus VGS with respect to VDS. Okay, what is the VGS here now? Can you see? What is the VGS? VGS is equal to 1.1 volt. Okay, VGS is 1 volt. The potential difference between the gate is at 1 volt and source is at 1 volt. What about VDS? It is nothing but 1.8 volts minus of IDS into 5 kilo ohm, right? Minus of 0. Source is at 0, right? That's the reason why it's 0. Now, can we say that what is the region of operation of this transistor by using these two equations? Which quantity that you should know so that we are able to tell that this transistor is saturation or linear? No. So if you know IDS, so this value is fixed value that you know very well. If this value is also some known value, then you can say that we can compare these two things and we can say that, okay, it's linear saturation. ID doesn't know. Okay. Then we have to assume the ID is whether linear or saturation. Once you assume something, and when we go on evaluating the things, we can say that whether it is in the correct, our assumption is correct or not, we can check. Okay. So now what is let us assume that the MOSFET M1 is in saturation. M1 in saturation. What is the current equation then? So we can write it as a half mu n Cox W by L into VCS minus of VT whole square. We know very well that what is this value they have given. What is the value they have given? 100 micro. 100 micro. What is this one? 2 divided by 1.8, I guess. Right? 2 divided by 1.8. Okay, micro will get cancelled there. This is actually 1 minus of 0.4, 0.6 whole square. Okay, 0.6 whole square. What is the result of this one? If you calculate this one, what is the result you will get? It is 200 microamperes. 200 microamps. If you calculate this one, you will get 200 microamps. Okay. This is how we said that we assumed that the transistor is in the saturation. Okay. Otherwise, you can start with assume that this is in the linear region also. It doesn't matter. Okay. But our assumption should be correct when. That means you keep this particular current in the VDS equation and compare these two things, VGS and VDS. If VDS is greater than that of VGS, then we can say that our assumption is correct. Is this point is clear? What I'm doing here? Yes, you said that current is 0. That means what is this value now? What is the VDS? What is the VDS here now? According to our assumption, this is 1.8 minus of 200 microns into 5 kilo. 5 into 10 to the power of plus 3. Okay, what is this value? How it becomes minus, madam? This is 0.8 volts. If you calculate this one, this is 0.8 volts. This is micron, right? So this is a 10th and will get cancelled. This value is very, very less actually. You know, it becomes actually 1 volt actually. 5 2s are 1. Okay. And this, okay, this is simple for a simple thing. This 3 will get cancelled. Another minus 3 is there. And here is actually, this is 10 now. The 0 will come. This 3 is also will get cancelled. This is becomes 1. Okay. 1.8 minus 1. It becomes 0.8 volts. Now this is what VDS. Okay. Now we compare this VDS with what? VCS minus of VTH. What is this value? 0.6 volts. Okay. So therefore, what we observe this one? VDS value is greater than VGS minus of VTH. Therefore, what is my assumption is correct or not? Yes, my assumption is correct. Therefore, MOSFET is exactly available in the saturation region. Okay. This is somewhat odd question that they have given because we are choosing something and do and go and so on and so forth. But this is what we have to do. So what is this question? Okay, we said that the MOSFET, the transistor is operated in saturation region. We concluded and confirmed that this is in the saturation region. Okay, later, for example, you may say that, sir, if I say that the M1 is in the linear, for example, I may assume it like that. Okay, then what is your conclusion coming to this point? You will conclude this IDS value, you will conclude. The current you will calculate. You put the IDS in the VDS and compare the VDS versus a VGS minus VTH, then definitely it should be VGS value, VDS value is less than VGS minus a VTH, it will become. Then you say that, okay, it should not in the linear, it should be in the saturation, you can confirm that. This point is clear? Right. Okay. So now the what is the pending question here? If I'm increase the gate voltage by 0.10 millivolts, a small change. Okay. If I'm applying the small change means that 0.01 volts that I'm applying. What is the change in the drain potential? So now, what is the value of the current now? 200. No, because of this increment of this one, what we can see for the M1. Now, because of VCS is equal to increased by 1 volt plus 10 millivolts, then what I will get then? What I will get? Therefore, ID is now, what is the IDS equation? We said that is in the saturation region, right? What is the current equation? We have to substitute in place of VGS, what value I have to substitute? 1 plus 10 millivolts that I have to add. If I do this one, I will get 206.7 microamps. Okay, this is what I'm just for the sake of time. I have given the value. Just only substitute in place of VGS is 1.01 volts. 1.01 volts that we have to add. Okay. Now, what is we can see now? What about this one? If I change this VGS value, what about VDS value? That's they are asking. What they're asking. What is the VDS here now? VDS is nothing but 1.8 volts minus of IDS into 5 kilo ohms. Am I right? Okay. Therefore, what is this value now here? 1.8 minus of 206.7 into 10 to the power of minus 6 into 5, 10 to the power of plus 3. Okay. This is what. Okay. We'll calculate that one. What is the value that we get? What we'll get that value? If we do this, this becomes 0.766 volts. Okay. What happened to this VDS value? What is the VDS value initially? 0.8. By changing the VGS value to certain value, then the current will changes automatically. Because of the current changes, what will happen to this drain potential of the transistor? It is reduced. Okay. Because of the reduction, is that mass transistor enter into the triode region? No, luckily by 0.7. What is the required condition to go into the linear region? Less than 0.6 volts. Okay, but it is more than the 0.6 volts. Therefore, still it is in the remains in the capacitor. Okay. If I say, for example, if you want to make this transistor operated in a linear region, what VGS that I have to apply. What VGS should apply here? How much VGS that I should increase so that it will enter into the linear region? That means I have applied a 10 millivolts I have increased. But how much I can increase so that the drain potential will go down, so that the gate potential will more, and so that the MOSFET enter into the linear region. Okay, we have to calculate based on that one. Okay, 10 volts, 20 volts, you can go 30 volts. But mathematically, what is this value? So it should be whatever the gate potential that you apply, you change. Okay. Therefore, that means this is the relationship you always remember. VCS values must be greater than or equal to VGS minus of VTH. That means VGS always more than that of the drain potential with one threshold voltage. If you apply whatever the VDS that is available, if you increase, add some threshold voltage to this one, that becomes if your VGS, then definitely the transistor will be enter into the linear region. That means it is less. It is less. So sorry, it is not less. It is greater. The VGS value must be greater than the drain potential by at least one threshold voltage. The MOSFET will enter into the linear region. Okay, that's what we have to understand about it. Of course, later we are going to talk about the small changes. This way of analyzing the thing is not sufficient. We'll go for the small signal analysis to identify whenever you change something, how much change that you can see in the drain, how much change that you can see in the drain potential and the drain current. All these things will come into the picture easily by using the small signal analysis. Okay, hopefully you catch this point, right? Okay, so generally we write this information in this way, but actually whenever you write like this, MOSFET. So where is the drain potential? This is called VDD, so highest potential. Can we say this a potential as a drain potential? No. Where is the drain potential? Here actually, right? This is the drain potential. Okay, this is the gate potential. And this is the source potential. Please remember this one. So if you see here, what is the drain potential of this one? What is the drain potential? Drain potential is nothing but VDD minus of ID. That means the current flowing through this one is called ID, because both are series. The transistor as well as the resistor, both are in series. That's the reason why same current will flow. Okay, ID into R. For example, this is called RD, for example. This is what I can see that one. So the potential difference divided by resistance is equal to current. This is how I can see. Okay. Now the question is, as we keep on increasing the VGS value in this case, what about the drain potential? If we keep on increasing the gate potential, or I can say that gate to source potential, what happened to the drain potential? So that's what we can say, that when VG is increasing, what will increases? It leads to ID will increases, right? If you increase the gate potential, the current will flow at a particular value of the VD, but if you keep on increasing the VG, then the current will increases. If the current is increases, what will happen? Okay, in this expression, this value is increasing. The negative side, that value is increasing. Minus of ID is increasing. That what is the result of this VD? This is positive. This is becomes therefore this end is actually increasing. That means the altogether VD value will decrease, right? The drain potential becomes decreases. VD becomes decrease. In this particular scenario, in this particular configuration, you have to say this is not true for all the circuits, right? But to all the circuits, true condition is that when the VGs increases, IDs also increases. But according to this configuration, whatever the drain potential actually is decreasing because of that particular equation. Okay, right. For example, if somebody give the ID equation, okay, that two saturation current equation have given. What is the responsible VGS that we have to apply to get that ID? What is the responsible VGS to get that ID? Okay, that means they have given, as I mentioned, that they have given ID current they have given. Okay, what could be the VGS to get that ID? What is the possible option? Okay, not this particular case, but actually not. I'm not saying that this is not the case. Therefore, this is what I'm talking about. For example, this is the MOSFET. Okay, but this reverse is not actually. This is not correct. But actually, let us understand this point. Okay. Okay, that means they have given here this one. But if you want to get this ID, what VGS should be applied? That's the question. How do you get this one? Assume that ID is in the saturation current equation they have given. Assume saturation current is given. Then they're asking you to calculate what is the VG to get that ID. It's simple. You can write what is the ID equation. IDS is equal of mu n Cox W by L into VGS minus of VT whole square, right? What is the VG here? You can observe this VD is available here. How can you get this VD? 2ID, okay, divided by mu n Cox into W by L. It is square root plus VTH is equal to VGS. Am I right? Look at this. I kept all the half mu n Cox W by L this side, okay, and now the right hand side the VGS minus VT whole square is there. To remove the whole square, the left hand side square root I have to give, and VTH is actually negative at the right hand side. It becomes the positive at the left hand side. Therefore, this is how I can. Is that okay? If you know the saturation current equation, if you want to find out what is the responsible VGS to get that one, this is the equation that you have to consider. So very important when we are talking about the circuits. Okay. So please remember this one, because we always try to work on the saturation region. Therefore, whatever the equations that are relevant for the saturation region, we have to take. Okay. So therefore, VGS is nothing but VTH plus square root of 2ID divided by. Sometimes I'm writing the small letters and cap letters. Please don't mind. Okay, this is all the pi center values. W by L. Something like this. Get this? Did you get this point? Right.